Buenas noches. Buenas noches, Salvador.
Buenos días.
Okay, so let's start then. So now we are going to give all of the formal arguments regarding the exterior derivative. And that's the operator G that we saw last time when we use it on forms, on differential forms. Okay, so let's see. So this is what we defined last time. We have k differential forms, right? We agree that on degree 0, the convention is that will be smooth functions. That is, a 0 form is a smooth function. Beyond that, so we have 1 forms, 2 forms, all the way up to n, which is the dimension of the manifold. Each one of these is a vector space over the reals. That is multiplication by scalar functions. And on the back side, they are infinite dimensional, so they are huge. Now, if you want another algebraic structure, each one of them, you can also think of them as a module. Instead of multiplying by a constant function, you can multiply by any function. But remember that this is not a field, so that's why it's not a vector space, but it will be a module over the ring of functions. But for the time being, I only care about the linear aspect and infinite dimensional vector space. And when we gather all of them, we will use this definition. Okay? So right there, you have all of the differential forms on the manifold of any degree whatsoever. Now, remember this, I mean, they are infinite dimensional, but when we talk about this, so this is finite dimensional, and this is also a vector space of finite dimension. Do you remember the dimension of that?
H of k.
Right, very good. So, and that's the reason that we stop at n, and there is nothing for n plus 1, n plus 2, and so on. Great. Now, the collection of all these vector spaces, we have this, and in fact, we have a product. We didn't discuss that product, but it's the one at the beginning of the book, and the same that you use on multivariable calculus, the wedge product. So when you use the wedge product, this becomes an algebra. Not only an infinite dimensional vector space, but it is an algebra. Okay? if you have a K form, and an L form, the degree of this is the sum. Okay. Well, now what are we going to do today is to define an operator like this. This is the one that we defined that we used last time in Euclidean space. But now we will define it on an arbitrary manifold, and we will see a few interesting properties of this. So the whole purpose of this class is to define this operator. It is called the exterior derivative and also the de Rham differential. Okay, so let's get to business to see what do we really mean by this. Okay, so this is the definition. So it is a linear map, and I mean here, this is the general setting, but we require that actually this happens. That is, if I take a K form, then this increases the degree by 1. Okay? So that's something that we will require on the manifold. On the exterior derivative. If I have a K form, then the differential will be a differential form of degree K plus 1. Increases by 1 the degree. We have a relation regarding the wedge product. It is similar to the product rule of a differential, right? So the whole idea is to make this be like a differential. Let's say something like this. Of course, there's no preferable x, right? But we think of v as a taking derivatives in some way. So number 2 is telling us the product rule. But it is the product rule graded. Because here is not always a plus. It could be a minus. So this K is the degree of alpha. So it is a product rule, but graded. The graded rule. The third condition, if we apply the differential 2 times, or the exterior derivative, we will get 0. And finally, we require this on functions. Because of this is a 1 form. I will require, if I plug in a vector, this should hold. So that's an exterior derivative on a manifold. We are taking derivatives of differential forms. So we will see that any manifold admits an exterior derivative, and not only that, it is unique. It admits only one exterior derivative, and that's what we're going to do today. Right? So let's use these four properties just to see what is D on a particular class of functions, namely constant functions. Okay? So this is my mistake here. F sub c should be the constant function c. Okay? So for every number, I have the constant function f of c. That is a smooth function. And let's see what happens if we apply a differential. Then, first of all, note that on functions, the wedge product is the same as the product of functions. So f of c is the same as f of 1 times f of c. Using the product rule, I get this. The degree of a function is 0. That's why here, and the mass will remain. So that means the exterior derivative and the constant function c is the same as this. But know that this one form is the same as this one. Hence, the exterior derivative applied to the constant function 1 has to vanish. Okay? And well, once that you know that this is 0, then for any constant will also be 0. So just from the definition of exterior derivative, we know what is the value on constant functions, which is 0. And that's more or less what we expect for a derivative, right? The derivative of a constant function has to be 0. So everything makes sense. Now, note that this argument that I use here, we have used it before when we define how a derivation acts on functions. We saw that a derivation acting on constant function vanishes, it's 0. And it is exactly the same argument. Okay? Great. So the exterior derivative vanishes on constant functions. Any questions? So again, let's continue. So the whole idea is to prove the existence of an exterior derivative on a manifold, and moreover, to show that it is unique. So that's what we're going to do. We will show the existence and uniqueness of a exterior derivative. And it is the same one that you saw in Euclidean space, nothing new. And we will use it, in fact. So the way to prove this is we will see what is D locally. That is in Rn, and then, so this is nothing new, it's the same thing that we saw last time in class. So that works very well on Rn. But now, if we use that part on a manifold, we have coordinates, so we can use the exterior derivative. But on a manifold, we have different charts on the same point. So we will show that it is independent of the coordinate system that we use. And finally, we will show uniqueness of V. Okay, so let's start by one. What is the differential locally or in Euclidean space? Okay, so let's consider the manifold to be the Euclidean space and take an arbitrary K form. This is how we can write out a K form this way. Remember that this is notation. Right? It is a multi-index I, that means this. And we always assume that they are in increasing order. There is no repetition because otherwise it would be 0. dx wedge dx equals 0. So that's why we put strictly smaller. Right? So that's how K-form looks on Euclidean space, the standard coordinate system. Now, I'm going to assume that we have a D. Okay? So this D satisfies the fourth condition that we enlisted here. Let me put it here again. Okay? So we will use this. Actually, yes. So those 4 conditions. And we will see that D doesn't have much of a choice to be something different. It has to be exactly what we have used before. So, okay, we replace alpha by this notation. We have it here. And then we use the fact that capital D is linear. So the sum goes out and I have D inside. Now, because D is an exterior derivative, now we use the chain rule. Okay? And I get this. Here is a plus, right? Because it should be -1 to the degree of what? of a function, but the degree of a function is 0. That's why we only get a plus. Right? Now, the whole idea is trying to understand Z on this type of objects and also to understand Z on functions. So if I have an exterior derivative, all that I care is what happens on functions and on elements like this, on one forms. So let's try to look at into that. Now, the coordinate functions are smooth functions, okay? So I can apply D and see what happens. Because this is a function, this is a one form. And my condition 4 of the differential, D of a function has to be equal to this. Remember 4? That's the condition number 4 on D. Now, remember that last time we saw this equality here, right? The dual, the xi is the dual, and we saw it like this. Hence, we now know that D on these particular functions is the same as this. Remember, I want to understand first this term, and then I will worry about this one. Okay, then all that we have seen is this is equal to this. So now I'm focusing on this here, which is here, okay? I want to understand D of that. But what we have seen here okay? Because remember, this is what I want here on the top. So I apply D on both sides of this. We apply D, and this is 0. Why? Why do I get 0 there?
Applying D twice.
Right, exactly. So we need to use the product rule. And when we use the product rule, we are explaining something like this. And using the fact that D twice is 0, everything vanishes. Okay? Very good. Now, remember, all of this was to understand d of alpha. We have seen that this is 0. So far, the alpha equals this. And now, again, we are going to use property number 4 on this, right? Same argument here, but now on functions. So this is what we cancel. And let's see this. So once that we cancel this, we know that D, capital D, all that I need to know is what's happening on functions. Because of all of the properties of D, we have this equality. If I want to know D on any K-form alpha, all that I need to know is what is D on any smooth function. But that's precisely number 4. Okay. So we get that D is exactly the one that we saw before in multivariable calculus. This one here. So on Euclidean space, if I have an exterior derivative, there's no other choice than this formula here. So those 4 properties forces D to be this one. Okay? So one way or another, we have defined the exterior derivative on Euclidean space. And you can also argue that we have defined the exterior derivative on a chart, on a manifold. But for that, still we need to think a little bit more. And that will come up next. So up to this point, any questions? Okay, so now we put aside Euclidean space, and let's see what happens on a manifold. Right, so just remember, on Euclidean space, any D will be this small d that we have seen before. So now let's consider a manifold, and let's try to understand D locally, only on a chart. So again, D is an exterior derivative. Let's pick a point, pick a chart. And again, any K-form looks like this. And then you might argue, okay, so let's define D as if we were on Euclidean space, right? And it happens that this is it is actually correct, although we need to prove that. But basically, if you have an exterior derivative on a manifold, then on a chart, this definition will make sense. That is, it's independent of the chart. So this is now our next task, to show that it is independent of the chart that we take. So make another chart. Obviously, let's assume that U and V have point in common. So we will have two different ways of viewing alpha, right? I can look at alpha using this on U. Alpha also takes this form on V. So on UV, alpha can be either one of those. Okay? Now, U and V are charts, so are Euclidean. So in particular, U intersection V is also Euclidean. So there I have a differential, and I'm going to write it like this, not only V, just to emphasize that it is on the smallest set U intersection V. Okay, then, so because this equality is on U intersection V, I apply the differential and I get this. Again, this is precisely the differential on the F and on the functions, right? So this means that we have exactly this, at least locally, we have it well defined. If I put a chart and I only look at what's happening on points in that chart, the D is well defined, regardless of which coordinate system I use. But now the problem is, well, I know this only locally in terms that we have a formula. So only when we put coordinates, I can have an analytic expression of V. Other than that, I don't know, right? So let's move forward and try to see and understand what is D. Now, well, we will use this fact, but okay. So the whole idea is we are looking at local stuff, but we want an operator which is global. What we did before was only we have a global operator and I know it locally. So that's why this definition is important, and it will be important when we try to understand D globally. So we say that this is local if for any differential form that vanishes on an open set, then D applied to alpha also vanishes on that open set. Okay? That's what it means for an operator to be local here. The idea behind this definition is, remember, try to think of the some partial derivative. Is a way of taking derivatives. Now, if you have a function that locally is constant, the differential has to be zero, right? So here, what we're saying is, well, I have a differential form, but on some open set, it is zero. Nothing happens. Then the differential on that same open set is going to be zero. Okay? And the way that we will use this is the following. I thought that I have written it down, but no. If you have two differential forms, again, this is something global, but you know something local. Assume that alpha and beta agree on some open set. Then, assuming that our operator is local, what happens? Right? But D is linear. Remember that they are always linear, so this is so that's like the main thing, and that's how we're going to use this property of the operator. The operator is global, takes any differential form on the manifold and does something. But here we have encoded some local information. If on some local space U, something is zero, the differential is also zero. And actually we will use is if two forms agree on an open set, the differential will also agree on that open set. Okay. Any exterior derivative on a manifold is local. Okay, so let's prove this. So take a differential form that vanishes on some open set. I want to prove that the derivative at any point on the open set is also zero. We want to prove this for any Q in U, right? That's the definition of local. Okay, so you have U, an open set, pick any Q, and take a neighborhood of Q. We will call it V, an open neighborhood. Now, let's consider a function that on V equals to 1, constant function 1 on V, and then on U, it will start to decrease, and the support of the function is inside of U. That means outside of U, the function is 0. Right? So this is the bump function. Consider f a bump function supported on U, which equals 1 on V. Then omega is a K-form. This again is a K-form, but that K-form is 0, right? Because omega is 0 on U, and F is 0 on the complement of U. That means that this is 0. That's clear to you? Okay. Then let's apply the exterior derivative. I get 0 in this. Then we use the product rule, and I have this. Okay? Remember, this is in all of M, so this is also on all of M. That equality holds everywhere in M. Now, let's see what can we say when we evaluate at Q, our point in V. So this would be this evaluated at Q. F of Q is equal to what?
One.
Exactly. And now omega on Q is 0, right? Because omega vanishes on U, and Q is on U. Hence, I only get 0, 1, and we are done. Okay, so any exterior derivative is local. Okay, well, this observation is what I made before, mean local, and this is the way that we will use that fact that V is local. Okay, so remember that this D is an exterior derivative given on a manifold. Locally, we define it in the usual way, like this. But D is global, but locally it looks like this. And now let's prove that it is unique. So let D prime be another exterior derivative on the manifold. Okay? Because this is also an exterior derivative, all that we have said also holds for D prime. So D prime is also local and blah, blah, blah. Okay. Take an arbitrary K-form, take any point, and a chart about that point. So at least on U, you have this. This is what we know, right? Because locally, we can give a formula for the D. Now, the whole idea is to prove uniqueness. That is, we will prove this, right? Remember, I took any alpha and any Q. And then I choose a chart and all of that. We will argue more or less as in the previous result. So I have Q. I take a neighborhood of Q inside of U. Now, this is on U. So here I have defined the functions fi and xi are only defined on the open set U. And again, I'm going to stress, the differential operators are global. So that's why we need to extend this form to all of M. So each function like this and each coordinate function, I'm going to extend it to all of M. I consider any smooth extensions of those functions such that on V, they agree. And then, I don't know, but eventually they might disagree, but they will be global. This is what is important about these functions. They are defined on all of M. Right? And on V, they agree. So then I consider a new differential form, given like this. Right? Because these are global and these are global, so I have that. And again, it is important that this is everywhere on M. However, on the smallest set V, we have that they are identical. Right? Now, remember that V prime is an exterior derivative, and what we just proved, it is local. Any exterior derivative is local. So, if this holds on V, well, sorry, I'm still not using, yes, so here I'm using that it is local. Remember how if alpha and beta agree on an open set, then the differential will also agree on that same open set. So these two are equal or identical on V, right? Now, because for alpha prime, I have a global expression, so I have this equality here. On V, we know this and this, and that's what I'm using from here to here. That's why there's no tilde here. I remove this and I remove this. Because now we are on the smallest set V. Right? But again, what we saw before, any exterior derivative of functions has to be the usual D. And that's it. They agree on V, in particular on the point Q, which was arbitrary point. So any exterior derivative has to agree with the one that we have defined. So there can only be one exterior derivative at all. I'm just rewriting the same definition here of the exterior derivative. So on any manifold, there is one, and it is unique. And usually we will stick with small d, okay? Usually that's the one that it is used. So let's review the definition again. First of all, so you should think of this as taking a partial derivative, so to speak. The exterior derivative increases the degree by 1. You have a product formula like this. this square equals 0. This will be also important next. And what is the value on zero forms or functions? Are there any questions? No questions? Now remember, so it is also very important to know how to do this. So tell me, what should I write here? This is on Euclidean space. We can do it step by step. So df1. But then I will need you to explain more here. I wrote a 1 form. Expand everything. What comes next? What is this? We saw that last time. So remember, this is wait, what am I doing here? F1. Like this. So this corresponds only to the first summand here. So this. And then I have to write the second one. Now I have F2. Again, F2. And so on. Now, many of the terms are going to cancel. Like this one here cancels, right? Because you have x1 wedge product dx1. And also this one here. dx2 wedge dx2, and so on. And if you want to write it down as we are using, so no, it will be minus oh no. This one here. Let's say that we have the convention to write it down with increasing order of the indices. Right? So I have to put a minus because I'm flipping dx2 wedge dx1 to dx1 wedge dx2. And actually all of them will be minus. And so on, right? I'm just trying to write this in increasing order of the indices. 1, 2, 1, 3, and so forth. Okay? Any questions?
When written in metric form, so that gives a antisymmetric matrix.
Again, please, Moises.
Yeah, well, what I'm thinking is that since the lead is a derivative, then it has to associate a matrix. I was wondering if the associated matrix is an antisymmetric matrix because we have that all the diagonal is 0, and we have alternating the, for example, we have f2, dx1, dx2, and in here we have the partial of f2, dx2, dx1.
Yeah, but I mean, basically that that phenomenon that you are noticing here is not related to the differential. It is related to the wedge product. So assume that you have V is a vector space of dimension n. This is my basis. For convenience, I'm going to take the dual. I have this basis. Okay, now I'm going to work with the dual V star instead of V. What's the dimension of this? Okay, because this is precisely generated like this, and then you go with E2. They have to be linearly independent. That's why I don't have E2 star wedge E1. And so you go all the way up to up to here. Everything okay, Moises? Now, so they are bilinear because k equals 2. And anti-symmetric. Okay. And then this happens. I'm going to take the first one here. First, I'm just going to evaluate on a vector u and a vector v. What is the definition of this wedge product? So you guys need to review chapter 1 again. This number times this number minus okay? Is what?
A determinant.
Correct. So what you were seeing here, I mean, it wasn't much of the differential. It's just the wedge product, what it is. And basically the wedge product, in some sense, the only k-linear maps that are anti-symmetric are determinants. So that's why you see that there's a determinant and all of that, but basically this pattern that you saw, it is here. And the other one that you can also see is this one here. And that's because the exterior algebra or the K linear maps that are antisymmetric basically are only K by K determinants. Determinants of K by K matrices. So this answer your questions, Moises?
Yes. Thanks.
So it is true, but not because of the differential, just of the wedge product. Okay. Any more questions? So the d, we will usually write it small d, and sometimes, usually we just write it d, but keep in mind that it depends on the manifold. This would be a more correct notation, but we simplify notation, we don't put the dependence on the manifold, and we just write d. Okay, so that's what we have. And now I'm going to review something that we also saw last time, but only on Euclidean space. Now this is on any manifold. So differential K form is called closed if it lies in the kernel of the exterior derivative. V is 0. And it's going to be called exact if alpha lies in the image of the exterior derivative. So note that here beta has degree k minus 1. Okay, so that's the notation that we use. And note this, so this is a subspace. Because D is linear, and this is the kernel. The same with this one. It is a subspace. Because it is the image under a linear map. So these two are linear subspace. They are quite big, so they keep being infinite dimensional. Okay. Now, an important an important observation is this, that every exact form, it is closed. Let's see why. If you take an exact form, what do you know? Alpha equals what?
D of B, beta.
Right. For some k minus 1. And then you apply d of alpha but you already know that double d is 0 by the definition of an exterior derivative. Okay? Now, this is the interesting aspect of all of this. So this is a linear subspace of this one. Both of them are infinite dimensional. But however, the quotient is finite dimensional. And let's write this, and here we will end the class. So I have a manifold of dimension n. So we're going to define a vector space. It is just the quotient. V is smaller than C. So this quotient vector space is the degree K cohomology. Okay.
What's homology? In general, what's homology?
Yeah, so we will come to that. So for now, let's only take it as a name. Okay. Now let's make a few comments on this. Either this or this. They depend on the manifold because they are defined in terms of differential forms. Okay, that's fair. But they also depend on the exterior derivative because it is the kernel and the image of that operator. But the good news is that what we proved a while ago, on a manifold, there's only one exterior derivative. So that means that this doesn't depend on any anything at all, only on the manifold itself. There's no additional thing that we need to do to define that. Because the operator was unique. So that's the good thing. Now, let's first make a few comments and then partially answers Moises' questions. Degree zero forms are what?
Smooth functions.
Pardon?
Smooth functions.
Smooth functions, right. Okay, so there we are. Here you have the T. There's nothing below zero, so here you can assume that you have this. And that arrow means that everything goes to the zero, to the constant function zero. On the other side, because of dimension reasons, we don't have any n+1 differential form. So here there's nothing. And we write an arrow and we mean everything goes to zero. Okay? Thus, so let's see. What is the image of in degree zero? What is the image of this map? It's just zero, right? I mean, what I said, that means that the zero goes to the constant function zero. That's the image. On the other side, what can you say now? You will like something that it is easy to see is the kernel. What is the kernel there?
The whole thing.
Yeah. So these are the two subspace that are easily computed for any manifold, right? Now, like this. And the other ones that are needed, so they will actually depend on the manifold itself. Except for this one, let's try to understand this. And this is because the definition of on this, remember? Now, I want you to think about this because I would like to know what is the kernel of this map. That means I take a function What can you say about that equation?
Maybe that all of its partials need to be 0.
Right. So we can choose a point and try to see what's going on. In that point, I have a chart. And relative to that, we know that uh, and in all of you, right? Then what can you say about F?
It's constant in U.
Okay, that's correct. And in global terms, what can you say? In terms of M. So that's correct. It's constant on U. But now, what's going on with F on the whole manifold M? So this is U. It's constant there. You can take other chart here. What can you say on that other open set?
It's also constant, and it's the same constant, right?
The same constant, right? Same constant. And then, what can you say then about F with respect to M?
It's constant on M.
Come again?
It's constant on M.
If I have something here, and there is nothing here, F is not constant. It is locally constant, right? It will be constant on each component, connected component. So what you have proved at this point give me a description of that set. The set of all functions on M that are locally constant. is like this only, or each number determines a locally constant function on M. Is that correct? Or we are missing more things?
Depends on how many connected components.
Right, so it will be R to the, let's say R. So is this correct for you? So let's see, you know that V0 is 0 and C0 is that. So you just prove this on degree 0 of n. My definition would be like that. Okay, so you know at least what is the cohomology of a manifold in degree 0. And the answer depends on the number of components of the manifold. Okay, so up to here, any questions? So by this, we will just think about information about the manifold M, but is topological information. So this is a vector space. I haven't shown you, but it will be finite dimensional. This is infinite dimensional, infinite dimensional. And so it's just some information about the topology of M. That's basically what by now we should understand about cohomology. Okay? It is something more general than that, what this word stands for, but for the time being, it's just keeping topological information of the manifold. Great. So if there are no questions, I think we are done for today. Yeah. Great. So we will continue tomorrow.
So yeah.
All right, see you tomorrow.
Okay, see you guys.